Let's continue. In the previous two examples, we look at how to convert transfer functions into state space differential equations or state space representation of a system. Now, in the first case, the numerator is 1 or a constant. And it's straightforward. One step, you basically try to find the differential equation first, and then select the three states. One is y, the other one, the second one is y dot, and the third one is y double dot, because the third order system we need three states. And then you find a relationship between them. And in the second case, there's a numerator term. And we sort of did this in two steps. We're going to we move the numerator terms to the front, and then dealt with the denominator term only, which is the process for that is the same as the first example. And the numerator term really affect the output equation, not the state equation. This example you're seeing now is the third case, where the order of the numerator is the same as the order of denominator terms. So we will do this in three steps. First step, we need to actually try to get rid of the s cube on the top. Okay, so what I'll do is that I will look at what is in the denominator and then make this up. I'm going to write the whole denominator terms up. Because I have a 2s cube, so I'll take the 2 out. S cube is that s cube. Then if I look at the denominator terms, I need a 6s squared. 6x squared, I write this down. 6s squared times 2, that's 12. But I only have 1s squared in my original transfer function. So I put a 12s squared here, but I only have 1. So I put a minus 11. So I don't arbitrarily add anything to there. So if I use a 12 here, and then I minus 11, then I have s squared. Third term, I have a 9s. 9s, I write this down here. 9s times 2, that's 18. But I only had 9s in the first place. So I put a minus 9 there, just to cancel the half out. Last term, I need a 6. 6 times 2, that's 12. But I got 20. So I got positive 8 left. So I put that in the second term. Now, once you've done that, you match the denominator terms here, then I can do a division. Because 2 times all that divided by the denominator terms equals to 2. So that 2 goes to the front. The second part of the numerator is minus 11s minus 9 plus 8 divided by that. So I write that down. Now, if you think about that, that's exactly the same format as I have in the second example. We have numerator terms, but the order of the numerator term is lower than the order of the denominator term. That needs to be divided into two steps. By moving the numerator term to the front of the fraction, deal with 1 over this first. And I'll deal with that two separately. Okay, but the second part of that is the same as the second example. Okay, so this is what I do. Let me or what we can do, not just what I do. I'll consider this as 2 plus all that. But transfer function equals to y over u. That's output over input in the frequency domain. Now y, I can divide that into two parts. I can have two parts of the output. One is y1. The other one is y2. So this y equals to y1 plus y2. Or y1 over u plus y2 over u. That's that transfer function. I'll make the second part equal to y2 over u. Okay, second part of that over equals y2 over u. Therefore, from what we discussed before, in the A matrix, I have -6, -9, -6. Basically, the first 9 is the coefficient of the last three terms, coefficient of the last three terms in the denominator, but you change the sign. So it's minus. Instead of 6, 9, 6, you put -6, -9, -6 here. Okay? And this is 1, this is 1. And this is 1 as well because you have output there. The C matrix in the output equation will have the coefficients of the numerator terms. So it's -11, -9, plus 8. So -11, -9, 8. That doesn't affect anything. So the state equation, the same as what we had before, we've done before with the denominator terms only. The output equation, there are now two parts. C matrix, or the values in the C matrix come from the numerator terms, x1, x2, x3. And by the way, the v and v double dot here are really represent the y2, okay, not y1, because we separate the two together. But where does that 2 go? Because we are without y1, just y2, this will be y equal to this times x plus 0 times u. But we are dealing with linear systems. They can add together. The output can be added together because y equals to y1 plus y2. y2 is what we have here in the c times x. y1, if you think about y1 over u equals to 2. Or y1 equals to u, or 2u, sorry. y1 equals to 2u. So y equals to, without the second part, this will be y1. But overall, y equals to y1 plus y2. Therefore, you put that 2 in the D matrix. Okay, so the extra term you got there, because you did a division there, just get rid of the s cube on the top. This number goes to the D matrix. Okay, so these are the rules. When you see a format like that, the last three terms in the denominator, so -6, -9, -6, that goes to the first row of A matrix. The numerator terms goes to the C matrix. This extra term goes to the B matrix. Okay, without this term, then D matrix. D matrix will be 0. Without this or that, this will be the number you put in the D. It will be 0, 0, some number, or 0, 0, 1 if it is 1. This would go, these three numbers go to the first row of the A matrix, but change the sign to the opposite. So this is what we got here. Because we define the three states, the second and third states are very simple relationships. Okay, this is y3 dot equals to y2, y2 dot equals to y1. So that's fairly straightforward process. So I will change this to y1 and then this to y1, this to y1 dot, this y1 double dot. After I finish my lecture, it bothers me. Okay, it really should be y1 dot, and y2 dot, y2 dot, y2 double dot, because this equals to that, this equals to the second term equal to second term, so this should be y2 dot, y2 double dot. I'll change that afterwards. Okay, so that's really how you find the cascade form of a state space equations. Okay, and I introduced three different formats, but ultimately they affect the A and B C matrix in different ways. Okay, so if you obviously to be sure, you want to go through the process I've gone through. But as a means to check if you got them right, and these are the things you should check. The first row of A matrix, what's in the C matrix, what's in the D matrix. B matrix is quite easy to check because you just check the input, depending on what input you get. Okay? That's a cascade form or classical form. We can also do it in the state space form. State space form actually we do not have to use different cases because whatever format we get out of the transfer function, we do partial fractions. We separate them into 3 different states. Okay, like the first example, 1 over s cubed plus 6s squared plus 9s plus 6. Now that's a third order, but effectively this is actually s plus 1 times s plus 2 times s plus 3. I've chosen numbers deliberately because I knew I would get that, okay? So you do the partial fractions, you get them into instead of 3 terms multiplied together, you do the partial fractions like what we did for the output response. Okay, you do a partial fractions, you find the coefficient A, B, and C using either the common denominator method or the cover-up method I introduced. Once you get there, now I consider, because of what GS is Y over U, that's transfer function, output equals to over input. I start to introduce 3 states. I just say YS actually equals to x1 plus x2 plus x3. So let xy equal to x1 plus x2 plus x3. Therefore, I get equation 2. Y over U will have to be x1 over U plus x2 over U plus x3 over U. And then I say this first term equal to the first term there, second term equal to the second term there, third term equal to third term there. So these x1, x3, x2, x3 are not only 3 parts of y, they are also my states. So to do that for the model form is a lot simpler. You just assume 3, even for a third order system, you need to break them into 3 parts. If it's second order, you break them in 2 parts. And you just assume the output equal to x1 plus x2 for second order. If it's third order, then you add x3 there. And then you just you just make the first term equal to the first part of the partial fraction, second part to the second part, third part to the third part. And if I copy all 3 down, so x1 over u equals to 1 over 2 s plus 1, x2 over u equals to minus 1 x plus 2, x3 over u equals to minus 1 over 2 over s plus 3. So 3 equations, and now basically I have 3 first order transfer functions. That makes my life a lot easier, because if I do cross multiplication for the first one, half times u, that's half times u, x1 times s, inverse Laplace transform give me x1 dot, x1 times 1, that's x1, inverse is x1, move to the other side, that give me minus 1. Second one, minus 1 times u, that's minus u there. x2 times s, that give me x2 dot, that's x2 dot. x2 times 2, that's give me 2x2. But if I move to the right hand side, that give me minus 2x2. Same for the third one. x3 times s, inverse Laplace transform give me x3 dot. x3 times 3, inverse will give me 3 times x3. Move to other side, it becomes minus 3 x3. Half times u, that's inverse of give me half times u in time domain. So easily I can convert 3 transfer functions into 3 first order differential equations. Now I'm ready to reorganize it because I know x1 dot equals to minus x1, x dot equals to minus x2, x3 dot equals to minus 3x3. So this coefficient minus 1, minus 2, minus 3 will just go into the diagonal elements, components of the A matrix. So it's minus 1, minus 2, and minus 3. This is x dot, this is x. Now, of course, now all 3 states are affected by input. So the second part of your 3 equations goes into B matrix. The first one, x1 dot, is affected by half of u, that's half of u. Second one, u2 dot is affected by minus 1, that's minus 1. So x3 dot is affected by half of u again, so half of u. So this time, A matrix comes from the coefficient of x1, x2, x3 in the first order differential equations, and off diagonals you get zeros because they are not, x1 is not affected by x2, x2 is not affected by anything else, x3 is not affected by x1 or x2, so there's off diagonal ones will be zero. But B matrix you need to fill in because every equation copy the coefficient of u here, coefficient of u here, coefficient of u there into C matrix. Sorry, B matrix. D matrix. See, the output equations are not easier because we assume that y equals to x1 plus x2, x3. So just 3 ones in the C matrix. And in that equation, y is not affected by u, therefore D matrix is 0. Okay, so it will be 1 times x1 plus 1 times x2 plus 1 times x3. That's equation number 3. So in this case, it's the partial fraction part is probably the hardest or the part that requires the most effort. Once you get there, then we will know the off diagonal ones in the A matrix comes from this pole, this pole, and this pole. So I have 3 poles here, minus 1, minus 2, minus 3. So that goes into the diagonal terms of the A matrix. Once you've done the partial fraction, what's in the numerator, half minus 1, half goes into B matrix. C matrix will be 1, 1, 1 because we are adding 3 states together to give us the output. D matrix will be 0. So in a way, that model form is a lot more straightforward. But sometimes the classical form has advantages. Sometimes, depending on your application, sometimes you may not be able to find the poles or find this you may not be able to organize that into this form. So the classical form becomes useful. But either way, it's state space equation or state space representation of a system, or sometimes we call it state space model, or sometimes we call it ABCD matrix. They are the form that can be useful in sort of modern advanced control designs. Okay, people often use these. Okay, so that's from transfer functions to state space equations. You can go backwards as well. If you have a state space equations and you want to derive the transfer functions, you can do that as well. And I have given some equations here. Say, for example, if I know A, B, C, and D, this would be the equation you use to derive the transfer function. Or that equation, there are 2 ways of doing it. Okay, this is determinant. Okay, this is determinant of this matrix. This is determinant of that matrix. It's either way. I've done some examples. I've given some examples here, but I'm not going to go through them because this is optional. People have less incentive to convert state space model into transfer function, but there's more argument to convert the transfer function into state space. It is possible, but it's less useful. So if you are interested as option, then by all means go through my slides here. And if you have any queries, we can always discuss. Okay, I'm quite happy to discuss anything you might want to be interested in. So anyway, I got some transfer functions for you, and I'd like you to derive the state space model of the system in both canonical form, that is the classical form, and also in the model form. Okay, it's just the way, and it's actually simpler than my examples because these are just second order systems. You only need two states, so that makes your life easier. Okay, so that will be my end of my lectures, and I'll give a revision session afterwards, and before your exams. Okay, I'll put a revision video on Blackboard as well, so you will see. I think that's probably next in your next scheduled slot. I'll do a revision. Okay, but I'll let you know. Okay, thank you.